Hi everybody, Mr. Rubo here. Today we're going to topic 1.7. We're going to start talking about rational functions and their end behavior, but this video is really going to focus on just rational functions in general, a lot of terms. So a rational function is simply the quotient or fraction or ratio of two polynomials. Okay, so the last so many topics were all about polynomials. Now we're getting into when we have a polynomial over a polynomial. Um, and because it's a fraction, the one thing we can't have happen is the denominator cannot equal 0 because we can't divide by 0. All right, so here are three examples of rational functions. If it's a constant function on top or bottom, doesn't actually matter. It is rational. Okay, so this is right here. It's a polynomial function, x plus 3, linear, which is also a polynomial. So this is rational. Next one, same thing. We got a quadratic over a linear, both polynomials. So yeah, and then the last one, a quadratic over a cubic. Again, polynomial over polynomial. So we have a rational function. So now let's go into the end behavior. So for this, the end behavior of a rational function is determined by the leading terms of the numerator and denominator. Okay, so in other words, if your polynomials in the numerator and the denominator are not multiplied out, then you want to multiply them out so you can figure out what the leading terms are both in the numerator and denominator, right? So the three examples here were all multiplied out. They weren't factored. If they were factored, you want to multiply them out to get those leading terms. So what we want to look at, there's a few cases here. So the first case is that the leading terms have the same degree. Okay, so in this case, n would equal d, so n being that power, d being that one. This one results in a horizontal asymptote, okay? And specifically, it's the a value, the leading coefficient in the numerator, divided by the leading coefficient of the denominator, okay? Case 2 is when the denominator dominates the numerator, okay, or in other words, is bigger. Then what we have is a horizontal asymptote again, but this time it's just at y equals 0. Okay, so just a quick example. If we wanted to say, let's say, find the limit as x approaches infinity, right? We're still using that notation of, let's say, this function, 5 over x. So the degree on top is 0, degree in the denominator is 1, which means the denominator dominates, which means that this limit is going to be 0, which means we have a horizontal asymptote. Right, and you could think of this as like as you substitute in really big numbers into the denominator, 5 over 1,000 is going to get small. 5 over 1,000,000 is going to get even smaller, right? So it's getting closer and closer to 0. All right, and then our last case is when the numerator dominates the denominator. Okay, this case, we're going to use long division to determine the end behavior of f of x. So you're going to take the denominator, put it on the outside, numerator, put it on the inside, and do the long division. If the degree of the numerator is exactly 1 more than the degree of the denominator, then the function, the rational function, has a slant, or what is also known sometimes as oblique asymptotes, or asymptote, sorry, just one. So you'll notice here that This is a very special case, so use long division to see what the end behavior would be. And then if it is 1 degree more, you're going to have a slant asymptote instead of a horizontal asymptote. Okay. All right. Thanks for watching. Have a good day.